Yes, first, of course, acknowledge your funding source. So Wrangler is actually the result of an NSF grant from the Division of Advanced Cyber Infrastructure, appropriate grant number. Thank you very much for the money. TAC is largely a cluster shop. I'll go through a little of the history here. We've done a great job supporting traditional supercomputing applications, but with Wrangler, we really wanted to take a new look at how we built machines around codes like the last speaker just mentioned in Xdata. So Wrangler is really a rethink of how we build clusters for these, quote, big data applications, which of course isn't one problem, but a huge family of problems that are somewhat related. And so, you know, as we all know, HPC and big data have a lot in common, and we can solve a lot of problems, but we can't really do every one of them. We thought about what were the gaps in our hardware capability. And so a lot of you know Stampede, our big machine, Xeon plus Xeon Phi. And it's a wonderful machine, really, for at this point, tens of thousands of users. But it does have some limitations for certain kinds of problems. And I'll go through a few of the ones that we've seen where it doesn't work well. And it makes a lot of assumptions about software, that if you're running, you know, Python code from Anaconda, it may not be the best place to work from. It assumes distributed memory. It assumes you use MPI-IO to scale up your I/O and things like that. Many of us have worked in parallel software. Theoretically, I don't believe that there isn't a problem that with enough time and effort of formulating the software we couldn't make run really well on Stampede. If we took your Hadoop problem and reformulated it as an MPI problem, we could rewrite some things and we could make that happen. But practically, that's never really going to happen. We estimate that on the current Stampede, 5,000 different binaries have run by users. So, you know, you might be able to optimize 6 applications or 12 applications, but you're pretty unlikely to be able to optimize 5,000 applications over a 3 or 4 year period. And even if you look at the big codes, the top 30 are less than half the cycles that run on that machine. So you really need to get to hundreds of codes to have any good chance of scaling up everything. So at the same time, I don't also want to define Wrangler as the bad code system, although it does do a lot to lift up codes that perhaps are not written optimally from an I/O point of view. But it will help with some weird things that we would never run well on supercomputers, and I'll do a quick example or two. And the other point we want to make around Wrangler is that for us in Wrangler, data isn't just a scratch object. It's the thing we're dealing with. It's a first-class object, and so we have support to keep it on the system for a longer period of time than we would on a scratch file system, to share it out, to do some curation work, to keep some metadata around it. We mirror the data to a second site, et cetera, all things we wouldn't normally do on an HPC platform that we think makes this interesting. And I should mention all of our partners. TAC is a part of it. There's actually a mirror of the storage that lives at Indiana, the University of Indiana. They're one of our partners in many projects. I think Dave's going to talk about one of the other ones a little later. But they host a fair chunk of the system with Chicago to deal with the Globus online integration and high-speed data transfer. On the vendor side, it's about half Dell and half a little company called DSSD, which during the course of the project, to make life more entertaining, was swallowed up by EMC. And so now it's an EMC Dell system. So backing up just a little bit, I think we've all seen over the last 20-something years, certainly since I got into clustering, we've gone from sort of, well, let's hack something together and find a way to make clusters work. That was the second Beowulf cluster ever built. We did in 1993, where, you know, I remember actually laminating the shelves that we put the machines on, right? And that was the standard ordered out of the back of computer shopper system, right? We don't operate at this scale in clustering anymore, right? We use, you know, the last system we did at TAC, Stampede, you know, 200 racks, the standard, you know, several 737s of weight, 10, you know, 5 megawatts of power, et cetera, right? That you expect in the big production infrastructure that we've built up around clusters over the last, you know, few decades. And we've gotten really good at that cluster thing where we can support a bunch of users. This is just some of the stats from Stampede. We hit 5 million jobs about 3 weeks ago on the machine, 1.5 billion service units, 2,300 different funded projects have run on it. So I'm not here arguing that Wrangler is going to make these kinds of systems go away, since this is sort of my main job. You know, these are still wonderful systems for large numbers of people, but we have other people in the community. And for those other people in the community, I would argue we're still at the garage cluster scale. and we have to get up to this production scale. And I used to have a bunch more slides that discussed how we've sort of rounded out the services over years, but I took them out and just let's cut to the chase on workloads. We've all talked about the big data workloads, the things we're analyzing in Python, looking at Twitter feeds and things like that. But we actually have a lot of I/O problems even in our conventional workloads. And so we do on Stampede keep stats on every single job that we run in terms of we don't necessarily show them all with the users. The way to become popular with users is not email them and say, your jobs really suck. At most of the ways they run. We use this to sort of target support in friendly ways to many users, but we keep a number of statistics on everything runs, including CPU fraction and LNet traffic, which is a pretty good luster proxy for metadata performance. And so this is a biophysics job, fairly standard of a huge amount of the workflows. And what you see is the job runs on for a couple hours, and in particular, if you look at sort of the bottom 3 graphs here, these two are metadata traffic, or good proxies for metadata traffic that suddenly explode, and the bottom one is CPU user fraction, which suddenly plummets as soon as the job starts doing metadata. So this job runs several hours longer because we can't support the metadata that it needs. And this is, again, not what you would think of as a big data job. This is an NWChem run from a particular user whose I/O is tuned so that same set of graphs, it pretty much has high metadata traffic all the way through the life of the job, and so the user fraction of CPU is less than 45%, and of course, it's not yielding that on the CPU, that's just the time that the job has the CPU, but it's cutting by half the amount of performance you could get just because it's waiting on metadata operations most of the time. And that's in WChem, not what you would think of as a big data application, right? A traditional HPC chemistry application. So, and then, of course, we have our favorite thing to run on big supercomputers, which I like to call the new failure mode that we discovered a few years ago, which is Hadoop. Hadoop really showed up in 2008, 2009. We were running it safely in some shared systems, but in 2011 is when users started trying to run it on the supercomputers incessantly. And you could always tell because your metadata servers would crash, right? Which is a good indicator that you have several users out running Hadoop. And the ones who weren't crashing the metadata servers were the ones who were using the local hard drives in compute nodes and the Ethernet management network to run it instead of the InfiniBand, and then publishing papers about their performance, which is great at 50 megabytes a second on your 200 gigabyte per second parallel file system. But yes, if you let users run Hadoop on your systems, bad things typically happen. We've done a lot to try and get Hadoop over shared file systems, and a lot of things have happened here. But fundamentally, we have these big systems that we've built with big central file systems optimized around large sequential access, a highly tuned, low-level programming interface that allows you to get remarkable performance out of those systems. And then we stick on this Java framework that assumes a small, massively distributed file system and is optimized for really, really small files. And only bad things can happen in that situation. And often they do. And now we've got them to where only moderately bad things happen, but it's still not good things. In fact, we have a dedicated Hadoop system at Tech called Rustler that we pretty much used some donor funds to deploy just so we could kick all the Hadoop users off the supercomputers and feel good about it. So they wouldn't destroy file system performance for everyone else running on the system when they were there. So to address these kinds of problems, crazy codes like Hadoop, and some even crazier ones, and just things that are limited by metadata, which we see all the time. And in fact, now we keep a list of Stampede users that do bad things to the file system, that Tommy Minyard, who runs Stampede, puts them on the banned list, and then we send them an email and say, would you like to run on Wrangler? After they do some bad things to the system. So we pitched Wrangler around in response to a lot of the recent, or relatively recent, NSF and PCAST reports around big data. I find a good way to win proposals is to figure out what people think the problem is and do that. The gist of these, and they use a lot of words in these reports, but it's more or less do something about data, do something about data at multiple scales. Don't just think about petabyte data, think about sensor data and mid-scale data, and do something that allows people to store things a little bit longer and do some collaboration, are sort of the 3 bullets there in lots of words. And so as we went into our design phase and sort of looked at community needs, we really found that, of course, as I mentioned at the beginning, data is not one problem. Data is a lot of problems that happen to involve bits. And it's a family of things we need to solve. So there's big and small data. Some people need reliable data. Some people are worried about the security of data. There's structured data. There's unstructured data. you need to be fast, but not just in our traditional sense of fast, meaning large files, sequential access. We need high transaction rates. We need random access. I think I'm probably preaching to the choir on this. We need Hadoop, but we don't need just Hadoop. Increasingly, we need Spark. We need R. We need GIS support. We need database support for relational. And we need to support things across the life cycle. And so Wrangler is really around those in mind. So here's sort of a bad high-level schematic of what it looks like. If you think of at least the TAC portion of Wrangler, and then I'll zoom out a little bit, there's really three primary subsystems. And one is a traditional disk subsystem that's sort of for long-term storage, but again, replicated, some metadata support, IRODS access. We'll store collections for several years on it. Starting out at 10 petabytes at each site. An analysis system of just a fairly small number of nodes. We've actually grown this out a little bit. I'll talk about that. It's now about 120 nodes. And then this high-speed storage system, which is really sort of the interesting part. It's about 600 terabytes of all flash in the DSSD product. We're shooting for a terabyte a second and a little over 250 million IOPS. We're actually up around 900 megabytes a second at the moment. So getting very close to that, which isn't, a terabyte a second is something fairly easy to do out of a big GPFS or Lustre or whatever GPFS is called today after IBM's announcements yesterday. But you can do it with a big Lustre file system. If you have 4,000 clients, you can get a terabyte a second. We'd like to get a terabyte a second to 90 clients. So it's the per client performance that we're really looking at. And again, we hit our 100 gig. It has a 40 gig to every node, because we do a lot of data ingest. And then a mirror to Indiana, where there's a second set of ingest nodes and another storage system up there. So just to run through them again, a little more than 20 petabytes raw, about 10 usable at each site, geographically replicated. That's not really the interesting part. Analysis, 2,500 or so cores. That's not really the interesting part. The interesting part is the flash storage. And we did not use SSDs. The nature of the DSSD device there, and you see a 72 terabyte device and a 5U chassis that they have there, is it's a big array of NAND flash dies, sort of a 3D RAID sort of configuration to tolerate a lot of failures. We haven't actually seen any flash failures yet. We've only had it up and running a few months. But there's about 100,000 NAND flash dies in the system. At the moment, we have 480 by 4 PCI links. We're waiting on one software upgrade to enable the other half so we can run them both simultaneously. But each one of these boxes has 96 PCI links, which led to our original count of 96 nodes. And so there's no actual interconnect. We run PCI cables from every node to every flash device. And so every storage byte is seen as local, which makes a huge difference, which I'll show in a second. And again, at the moment, we're using about half of them in the current system. So we have 10 of these D5 devices. And again, that gives us around 600 terabytes of usable flash. And we don't treat it as a cache to the disk. It's just a separate file system. If you're working out of here, you're working all in flash. And so good things happen with that. We mount the flash in several different ways. It's fairly dynamic. So we've actually partitioned it up a little so we have some persistent file systems. We can, on top of this flash interface, at its lowest level, it's an object store. That's the native one. And it does 4K puts and gets, and remarkably quickly, as I'll show. But we also can make it available as a traditional file system, an HDFS file system if you're in the Hadoop family, or on top of that, we just run a block driver on top of that object store. So we can also make it a relational store and run databases on top of it. And so we have sort of small permanent ones, and then we have dynamic volumes. We do a lot with reservations in this that we don't do in the traditional machines, but you can go into the portal, set yourself up a job, make a reservation, and it will create either a database or an HPFS file system or whatever you want to run on, and we can set that up in about 30 seconds across them. So at this point, Wrangler is in an early operations mode, which means we have half a dozen different projects using the system right now. We're adding 3 or 4 projects a week. We're waiting for one software upgrade that will get us to sort of what we consider full production. We're getting about, we need to get, there's 10 devices, 20 controllers, 2 controllers per device. We want to tune to about 50 gigabytes per second per controller to get that terabyte a second. We're getting 46 gigabytes per second per controller at the moment, so we're very close to that. And we've, just based on the first couple of months of experience with it, there's only 96 physical ports, so that's sort of a hard limit. But we decided to partition the devices up into several pools to add some more nodes, because we see a lot of things that are relatively small. We'll have 48 nodes that can see all the devices and work at the full 600 terabyte scale. But having groups of nodes at 200 terabytes and some persistent storage has actually worked a little better for the users. So let's just get to a little bit of data about what it can do. So this, on your left-hand side of the graph here, this side, and note the units here. I couldn't put these on the same graph because this is in tens of megabytes per second, and this is in thousands of megabytes per second over here. And this is traditional Lustre for 1 megabyte and 128K block sizes, single client performance, right? One thread doing I/O. And you get tens of megabytes per second out of Lustre. And if you use lots of threads and lots of nodes, you can get to hundreds of gigabytes and scale out to a ridiculous amount. This is the DSSD all-flash single thread I/O, and we couldn't actually make the 16K block runs finish in finite time on Lustre. But this is for a megabyte, 128K, and 16K blocks, and you actually see the megabyte and 128K is almost the same, right, for the different sizes. And you still get reasonable performance down at 16K, right? We're at 1,500 megabytes per second here for sequential read. We were at 20 megabytes per second by 128K on Lustre. So it's dozens to hundreds of times faster per thread, for all of those bioinformatics applications, say, we talked about yesterday, or Python applications that aren't massively parallel and that are transaction bound because they're going through, tweets and files, very small, 128 byte accesses and things like that. We get several hundred times the performance that we would get out of a disk system. This was just from the early prototype system. Same thing, just doing writes from 40 megs down to 4K. Disk, a traditional SSD, an older admittedly SSD. The new PCR card ones are better. And then the DSSD flash box, which is not SSD but has SSD in the name, very convenient. And you see it, 40 megabytes, and this is logarithmic, by the way. We're 5, 6, 8 times better than disk, which is nice, but it's at 4K where it gets really interesting, where suddenly we're hundreds of times better than disk and maybe an order of magnitude better than traditional SSD, where you're still limited by the SAS interface, even though you have flash under the hood there. So pretty dramatic difference in performance. This is almost the latest. I don't have quite the latest graph of performance. We've really been working on reads lately, so reads are doing a lot better, but this is just showing that at, even with just 20 or 30 clients, we can get up to 46, and this is over the direct interface, the native object store, but we can get to about 46 gigabytes per second of sustained read throughput. So just a few minutes to go. Let me just say I want to come back and just do an example or two of early science, but the parts are interesting, the hardware is interesting. We do pride ourselves on a project being more than just the parts and the set of services we put around it. To do this, we have a very different user base in this, and we're finding some gaps in our services and things we need to do better at. But we do have sort of an extended support service. We've always done this in Exceed. Every HPC center does some version of this, right, where the idea of taking an HPC expert staff member and pairing them with a team over time. We do that now with one of our data team members to pair them with a team. We're using a lot of the Globus online dataset services and a lot of the metadata tagging in iRods. We do a little of what we call auto-curation, just building metadata tags as we go through so that you really can treat the data objects as collections and share them at the end. We've worked on a fairly wide, I think all of these words have appeared on some slides yesterday and this morning, but to have support for things that we don't always support well on the regular supercomputers are Python, Mesos, GIS support, Spark, et cetera, et cetera. We're doing some end-to-end network performance tuning. We are actually taking data via shipping disks, as was discussed yesterday. That's a box of genomes in from the Philippines that was actually sent to us, and the box actually was that dinged up when it arrived. But getting data into the system is obviously a big concern. Little known fact about Hadoop. I don't think I put this benchmark up here, but our input speed is about 100 times faster than we were getting out of our traditional Hadoop system, our all disk-based original Hadoop system. we could only import, it was something ridiculous. It was measured in megabytes per minute with the actual import rate, because Hadoop import is not only in Java, but single-threaded to any Hadoop file system. So to actually load a 600 terabyte Hadoop system would take 10 months, which is less useful than you want. So we've done a lot to enhance input. So given the time, let me just dive into one deeply, and then I'll show a picture or two from the others. But this was the first big project we put on there. It is a bio case. It's one of these crazy codes. It's called OrthoMCL, which is the standard code that we have to deal with because none of you have probably ever heard of it, which means it's had no sort of performance optimization, and I'll explain why in a minute. But it does orthologous protein comparison. So there's several different projects. One of them is looking at brain development across different vertebrates. I forgot to bring the publication titles. One of them is looking at the alkaloid development in plants, but you can use it for a whole bunch of things. There's actually a fairly big community that we never heard of around it. It runs BLAST and some of those traditional things. It does have a fair amount of computation, but they decided to do all the comparisons in Postgres tables. So most of the computation is inside the database, which is why no one in the HPC world has ever tried to optimize it. Because if somebody tells you they did most of their computation inside Postgres, the correct response is, don't do that. But we don't have time to do that for thousands of codes and thousands of users. So we built a system that can do it. The databases that they're using are tens to hundreds of gigabytes, which is not big from a big data perspective, but if you're used to working in Postgres, that's a lot of Postgres data to do table operations on. And so our experience on it, so I'm into my final minute or two, is they had some developer benchmarks that were on like 100 megabyte data sets, and they claimed they could run those in 24 hours. And we were trying to run something about 100 times larger. And so we had tried to run this for several weeks before we got Wrangler going on our traditional Corrals, one of our big shared storage systems. We have just some virtualized service across it. And we were running, there's about 30 steps in the benchmark. Some steps were taking hours. Some steps were sort of never finishing. They'd run for 48 hours and time out on the database. We called the developers for this code and said, so we have this data set, it's about 10 gigabytes. They're like, yeah, that's never going to finish. There's no chance our code can actually do that. We put it on Wrangler, and we went from the developer said it would never finish to getting them all done in under 6 hours when we actually ran them. So, and the developers are now very curious about it, but again, has great ease of use, has a nice little portal in front of it. It's really easy to run the code, but it does all of its computational work in the database, all random access, all about data throughput except for the BLAST stage. For those particular projects, they'd spent about a month frustrated trying to get things to run. We put them on Wrangler, and in less than a week, we'd completed all these runs, 4 to 6 hours, as I mentioned. There's already 2 papers out from the results of this, again, in brain evolution. And there's a whole bunch more users at various different sites that have started doing this in the field that I had never heard of called sociogenomics that runs through this. But again, typical example, this is something that if they came into your front door as an HPC center and said, I have this code that does all its computation in Postgres and is written in 4 different languages, and I need to scale it, you would say, let's just start over. And there's a limit to how many times you can do that kind of thing, right? And just start over. Wrangler gives us the ability to just run those codes. And so we're looking at a few more examples, a lot of genomics, obviously, a lot of things that we've been building RAM disks to try and hack around to run. We can run natively. We're doing some fMRI data. We have a lot of text image data. This is a Viz steering one where on our old Viz system, 256 GPUs, which is great, but it takes 3 hours to read 17 time steps off disk to support it. We've done it in under a minute. On Wrangler for, again, a more traditional computation one. So there's lots of these problems out there in the world. We'll skip some of the lessons. And really this flood of new users that we're seeing that are stressing our support systems on the old machines, that are stressing the hardware on the old machines. And so Wrangler is our attempt, again, to just build hardware that supports them better and change our support and services model around that. So with that, and it's one of a whole bunch of things that we run now. So let me just stop there and say thanks, take a few questions before the break. So.